Thank you, Angelo, for the introduction. Welcome back, everybody. So, in the previous two editions of the hands-on workshop, there was only one talk on data analytics, machine learning kind of things that I have been giving. And as you see today, there is a full session, and actually there is also another talk by Michele Ceriotti on the last day that is, again, data analytics, machine learning, dimensionality reduction is one aspect. So today I will focus only on one aspect of data analytics, that is kind of umbrella name for machine learning, compressed sensing, data mining, and so on. And the general motivation, so Gabor has already a little bit distinguished between two different ways to look at the machine learning or data analytics problem. Actually, I will also have a slide on these two ways. Let me start by saying what we want to achieve by using the methods that I will be presenting in this lecture. The idea is to kind of accelerate the discovery of new materials. And by using computers and algorithms in such a way that we accelerate what has been done many times in the past. One notable example is the periodic table of elements. And I like to show the original, actually the second version of Mendeleyev's periodic table of elements. There were many competitors at that time. Mendeleev was the winner because nowadays we know why this table is correct. And he fancied something that looks very similar to the modern table by just looking at how elements react with, so the stoichiometry of the reaction with oxygen and hydrogen, and just by using the atomic weight. That was what was known. Of course, they didn't know anything about atomic number by then. So the amazing thing here is not only the structure that is very similar to the modern table, of course, if you abstract a little bit, but you see that the columns and the rows are basically the modern ones, but the fact that Mendeleev predicted missing elements. So he says, well, between zinc and arsenic, there is something in between because I don't see anything with this atomic weight that reacts in this way with oxygen and hydrogen. And years later, people found gallium and germanium with a pretty good prediction of the actual atomic weight and behaving exactly as they should on this table. So the periodic table of element is done. There is nothing more we can discover. Okay, we can have something a bit with higher weight on the table, but not very useful, I think, for material science. At least on Earth. But we may want to build a chart of materials now, so a combination of elements, and predict how they behave. So the goal, oops, this was left from another talk, so is to predict materials properties. And I will show something about the prediction of ground state of crystal structures. Here in this talk, novel topological insulator, not materials. And also whether material is a metal or non-metal. But first I have to introduce the methodologies to do this. And then on the long run, we would like to aim a bit higher and predict the materials for actual useful application, right? So targeting an application, find the best material doing something. So as I was saying, Gabor has basically already said this thing. I use a different wording, but the same concept. So there are basically nowadays two approaches that I think will merge in the near future, actually. I call one the configurational way. So that basically is machine learned simplified many-body Hamiltonians, what you call these surrogate models, right? And in this class, I would put cluster expansion. You will actually see tomorrow. You will have a full tutorial on cluster expansion, the Gaussian approximation potential, kernel ridge regression using Coulomb metrics or other kernels and so on. The idea is that you use you define a chemical space, so you have some chemical species. And importantly, you have your training material is list of labeled configurations. So you have configuration to which you attach some information that you have and you want to learn. And you want to learn some property that typically is the energy and forces. Typically in this field, people are after potential, empirical potential or force field. You have seen that it is quite successful and under active development. The problem may be that if you learn something for a specific set of chemical elements, you may have hard time in transferring what you have learned on different chemical elements. Sometimes even changing the composition could be hard if something has been missed by the configuration. The other approach, kind of complementary, I call it the chemical space way, and basically will be devoted on this approach in this talk, and it is also my main research topic, is try to learn physical rules. I dare not really call them laws, but at least rules, in order to predict properties, in some way also take into account the configuration, because at the end of the day, atoms have to be in some configuration in space before they can have show some property in a class of material. So here, differently from here, we have the input as list of labeled composition. So we have composition of material that has certain value of a property or is classified in a certain way, and you want to predict the property for things that you have not seen yet. Well, you start from predicting from what you have seen already, just to validate the model, or train the model, sorry. The problem here would be that if you don't have any information about the configuration or the structure of things that you are investigating, if there are polymorphs, so things with the same composition and different structure, you may be missing that if you don't give this information explicitly, or you find an indirect way to give this. But again, so we would like to have this learning. So I give you a composition of a material and you say this is a superconductor or not, or better, I give you a class of materials that are superconductors and not superconductors, and you find a new one that has not been seen, new composition, new material. That is a superconductor, for example, yes. Okay, I have a guinea pig kind of example in order to introduce the methodologies that we have been using. So this is the prediction of whether a certain class of octet binaries form a rock salt or zinc blende crystal structure. So the octet binaries are made by combining the first with the 7th group, second with the 6th in the periodic table. If you stare a little bit, you see that this periodic table is a little bit strange. I put copper and silver here because in this kind of example, they behave like 1s and these 2s, 2s. So I took out a couple of elements from here and put there for my amusement. And so if we want to predict whether these things form rock salt and zinc blende, it may not be trivial. I mean, it's easy to predict that if you combine this with this group, you get a rock salt because that kind of bonding is ionic. And if you do a combination of carbon with silver and so on, you most likely get a zinc blende because the binding will be covalent. But in all the other cases, that might be not easy. Now, we want to predict if something crystallizes one of the two structures. Let's use the periodic table, actually even less than periodic table, just the information on this atomic species, atomic charge, and I color red zinc blende, blue rock salt, and green those that are a little bit in between the two structures, so the energy of formation of the two structures is almost degenerate, according to the LDA calculation, just to make it clear. And okay, you see that there is some structure for the groups and periods in the periodic table, but it will be difficult to predict something if you remove some data points or even a full group of data points, whether this will be blue or red. What we would like to have is a chart. So something which everything here is rock salt, for example, everything here is zinc blende, and even more interesting, everything that is in between is really in between, so that we don't misclassify things. So this is, I said, is a kind of guinea pig example, but it's not totally trivial or without any interest. There have been many people that have been thinking about this problem and publish as a consequence, starting from the late 60s. All these people, except this paper here, have been using their chemical intuition and understanding. We would like to, and they found solution. Actually, I show one in the next slide. We would like to automatize these things, and in particular define exactly what we mean by this chart of material. So a bit better than just saying I want blue here and red there. So if the atomic number is not enough to predict properly, one may introduce new players in the competition, and which player depends now on your chemical physical intuition. What I present from a certain point on is just some machine learning, compressed sensing that compressed sensing people do not like to call it as part of machine learning, but let's say as a matter of fact it is machine learning. And this is some automatic algorithm, but the beginning, setting up the physical problem is our intuition that does the job. The same way for using machine learning for learning a force field, the potential energy, one has to think first what information to do. Giving the coordinates of the atoms in space is stupid, because you ask the machine learning to learn the symmetries, for example, while we know before we start that there is translational rotational symmetry. Why should we ask the machine to learn, if ever will? So we have to put our knowledge and intuition. Of course, knowledge and intuition can be also biased and can lead to unwanted paths. Okay, so back to this problem. What is more than atomic number, but not too much, because I mean we want just to predict whether these people do rock salt or zinc blend. So we don't want to use too much information like we make rock salt and zinc blend, calculate the energy, and then we want to predict whether they are rock salt or zinc blend. I mean, you already know the solution, so you shouldn't do that. So what is less complicated than the crystal structure, but more complicated than the atomic weight? Well, some property of the atoms, isolated atoms, that are calculated with the same Hamiltonian that you use to build the crystal. I mean, eventually you want to predict what happens in nature, so you need that your Hamiltonian is also good for that. And then you may use HOMO, LUMO, ionization potential, and the extension of valence orbitals that you calculate with, for example, LDA kind of Hamiltonian, and predict the difference in energy between the two structures. This is the continuous transformation of the problem of classification that is better suited for calculating what is on the boundary line. Here I just remind what we are talking about these properties here. So if you have the constant level for one atom, you have the valence up there. I zoom in, and you have the HOMO, the LUMO, you have a P and S kind of levels, and for each of them you can take out the radial probability density, so of the specific orbital, and define some radius, for example, the one at which this radial probability density is maximal. And this would be one possible way to describe your atom and use this information for prediction. So this valence and S and P orbital actually is not a new idea, not from me at least. It was used heavily in the past. From the early 70s, people started messing around with this the atomic descriptor in order to predict whether you will form a rock salt or a zinc blende or other structure. So this is the original figure from this paper in 1978. I colored it just to make it a bit more clear. And by using this clever linear combination of Rp and Rs for the atom A and B in this octet binary, people, well, not only Chelykovsky physics, but many others, have done plots like this, in which you have regions of rock salt, zinc blende. So this is a chart, right? If you get a new material that lands here, most likely that would be a rock salt. if you get a new material that lands here or here, well, okay, here maybe there is something that you have not seen yet. Here, well, you don't know if you are in the white between here, among here. But still, this is kind of charts that are kind of ubiquitous, especially in materials engineering. So you find a lot of these materials charts to predict property of material, and that most of them, at least until the, I would say, late 90s or beginning of 2000, were done by hand, by intuition. So we would like to kind of do this chart of materials automatically. So how do we do that? We start from a training set, so something for which we know already the classification or the property that we are after, calculated with some method. Here, what I want to stress is that the training set has to be consistent. So the properties calculated or measured, if one wants to use experimental data, with the same methodology, and you trust that there is the same methodology. Because if you introduce random error due to different methodologies used at once, and even different convergence levels with the same methodology, if you're using DFT, that can be hard for the machine to distinguish between what was just a systematic error and what is the actual thing that you are after, the actual property that you are after. Next part, and actually the most important, is to find a descriptor. So you have already heard 2 talks about this. What we aim to do here is to find the descriptor automatically with some preliminary considerations. So once one has a descriptor, so a way to identify typically numerically a material, one can make a table in which you have each line is a material, then you have a vector that identifies your material and your property. It is a scalar because typically you are after a scalar, but could be also a bit more complex. Then you invoke statistical learning in order to find the model that binds the descriptor with the property. And the catch is that this model, once it is learned, is much faster than what was used to calculate the points here. I underline once it is learned. It could be that to learn it takes quite a while, quite a lot of computer time. But when you have the model and then you can use it, that's fine, because then you're faster. And you can predict something new that you have not seen before. And you want, at the end, to close the circle, check if what was predicted new is consistent with what you have in the reference. So my methods that I will be describing here, the first one is compressed sensing. And it starts with an ansatz that should be familiar to physicists, that is, okay, I don't know anything about the property that I want to calculate, I expand it over a basis set. Except that here, normally we don't really know what is the basis set. So P is the property, T are the basis functions that we call also candidate features. You will see in the next slide what are these. That are function of some input features that we put. Then you want to learn these coefficients. Same way in kernel ridge or a Gaussian process, you learn these expansion coefficients. So your basis function are the Gaussian over the data points or some of the data points. Here you want to learn these coefficients. The catch here is that you want that only few of these coefficients are different from 0. So you want that this basis set expansion is as compact as possible. Why? From a mathematical point of view, a small number of coefficients here makes the model robust, so you avoid overfitting, what Matthias was talking about in the talk before. From a physical point of view, well, maybe you can have a final expression that is easy to look into and debate about, so if it contains some physics. The other method is called subgroup discovery. This comes from data mining. For this, we had a collaboration with the Max Planck for Informatics in Saarbrücken and the University of Saarbrücken, so the group of Gilles Freken, and in particular a postdoc of Gilles Mario Boley that was at the Fritz Haber for 1 year while developing this methodology. This is a very clever method that tries to find local models rather than global models. So typically what we do is to find a model that is good for all the data that we have. And in this methodology, we aim at finding models that are good for a subgroup of data, but we want to discover also which subgroup on the fly. That's the catch, otherwise it would be easy. You just learn separate models, and that's it. So I start with compressed sensing with a small forward on dimensionality reduction. I guess Michele Ceriotti will be talking a little bit more about dimensionality reduction. But I want to introduce dimensionality reduction because, well, it was used in the past. And second, this problem here looks like dimensionality reduction. So if each basis function is one dimension in your representation, when you do the compressed sensing, you want to find a low dimensional representation. So you want that only few of these coefficients are different from 0 when you represent your data point. A different approach is the linear dimensionality reduction that has quite some historical importance, but is still used here and there. I guess Matthias didn't go into these details, but dimensionality reduction is used also in kernel ridge because you don't want to have too high dimensional things flying around. So for lecture tutorial purposes, I think you must know principal component analysis. Most likely you have seen already, but let me just say what it is and how it is used in this context. So it's nice to have a paper from a very long time in the past that is still can be cited in a lecture in 2017. So this is by Pearson. And the principal component analysis works like this. So if you have a representation in high-dimensional space, you want to look for the direction in which the data are most elongated. So the standard deviation of the data, the variance, along that direction is maximal. So if you think about the cigar in high dimension, you are looking for the axis of this cigar. And then you want to look for subsequent dimensions in which, taken out the first, the data are most distributed. So direction and orthogonal direction means that what we are doing is a rotation in the high dimensional space. And then we take only few of these dimensions. So look first here. That means that this makes sense if the projection along this dimension that we find quickly dies off with the dimensionality. So if the data are spread over a hypersphere perfectly in the high dimension, then there is nothing that is most relevant. But if it's like a cigar or something that has a few relevant dimensions, you find them, then you say, okay, my data live on a kind of hyperplane with low dimension, and I can describe it. So this was actually used in the past for the problem of classification of rock salt versus zinc blende by using this as input. Valence number, energy of valence S&P, radius of valence S&P. So, and then some combination of this above makes 8 dimension. So you represent your materials in 8 dimension. You look for the principal components. Typically you like that these are 1 or 2, because more than 1 or 2 is difficult to make a plot out of it. So with 2 dimensions, you get rock salt here, zinc blende here, and other classes, Wurtzite, that is, let's say, like zinc blende for the first neighbor shell. So there is some structure, some separation, let's say covalent here, ionic there. So it's a nice representation. If you get a new material that lands here, you are almost sure that it will be a rock salt on the basis of this. The problem here would be what is on the axis. Well, it's a linear combination of all the input because we have done a rotation in the high dimensional space. So this is a kind of chart of materials, not so useful for the insight because we don't know what is on the axis. We can write it down, but it would be almost useless. There are non-linear dimensionality reduction strategies, and these are even worse from the point of view interpreting what is on the axis, because normally you don't even have axis. You will see with Michele Ceriotti. They are useful, very useful, this representation for other purposes, not for understanding why certain material would be in one class or the other. Okay, back to our method and think about the dimensionality reduction in the background. So we have this input, And now we want to solve this problem of finding a linear combination of the above such that they can predict the property, with the constraint that we want this linear combination as low dimensional as possible. So few coefficients are different from 0. And then I add already another player here. I add non-linear. I thought I changed this slide. Okay. Focus a bit on the thousands now, not on the billions of nonlinear function above, of the above. And this is done by what is called, well, borrowing the language of symbolic regression. Symbolic regression is a way to try to fit data, not with an answer on how the function is done, like linear or something else, but by trying to learn also the function itself out of a set of functions. How do we construct the function? This is where I borrow the language from symbolic regression. Well, I start constructing the grammar. I make sums or absolute values of things that are the same. So if I do sum or absolute values, I don't want to sum a radius with an energy level or something that doesn't have the same kind of meaning. So I have to define class of quantities. So a grammar. Then I may want to take ratios, and now it's fine that I take a ratio of radii, sum of radii divided by absolute values of some levels. It may sound a good physical equation, and then you introduce new operators, exponential powers that you can put here. The reason I write this as a tree is because this is the way you code it. The nice thing of this representation is that if you take out one node of the tree and you substitute with another subtree or tree, you always get a well-formed expression. So this is a way to propagate huge formulas without thinking too much. You have just to pay attention to the grammar of the last level when you form it. This is also not a new idea. People have been using this symbolic regression, but just a stochastic way to find the optimal solution under certain condition in something that is called Eureka, that is actually a proprietary code and is a genetic programming software. It exists still. I mean, it was a science in 2009. And you can use it. And this is an example of application in 2014 in which Tim Mueller wanted to find what predicts whether certain amorphous structures of silicon atoms have a certain hole trap depth that is interesting in some applications. And this is the list of some of the candidates. There were a total of 242 inputs. And this was the final formula. So you can use this stochastic approach. The problem here would be that, yeah, it's stochastic. So you're exploring a huge dimensional function space in this case. By following which formulas are more promising and substituting pieces. So there is absolutely no guarantee that you are going in the direction of the global optimum. You find expressions, yes. And if you're fine with it, that's fine. What we used is a different approach. So we wrote this the problem in this way. So we want to find the coefficients here that make this linear prediction, P equals CD and so on, as small as possible in terms of root mean square error, with this so-called regularization. So we pay a penalty every time a coefficient is different from 0. And this is written in mathematical terms with this 0 at the bottom. I rewrote the problem here. So this just means that we want to minimize this under a constraint that the number of non-zero coefficients is as small as possible. This is actually what we want to do. This is called regression with L0 regularization. It's fine. The problem here is that the only way to solve this exactly is to enumerate all solutions with 1, 2, 3, 4, 5 non-zero coefficients and compare them. With 1 or 2 maybe doable, the more you add, the thing explodes combinatorially. So typically with this sensible number of D columns, this is not doable. So we need a way to approximate it, but to approximate it in such a way that at least we can continuously go to the exact solution if we tweak some parameters. And one way to do this is using the so-called lasso. It's an algorithm in which we substitute the 0 here with the 1 here. So the 1 means that we have now the Manhattan norm, the sum of the absolute values of the element of C. So with this regularization under certain condition is the same as this one, but the problem becomes convex. So now we can do much better optimization. Also, this is not a new idea. There are papers in the recent past in which people use this approach in order to basically find good basis sets for a cluster expansion. You will see cluster expansion tomorrow, and I guess also some of these ideas. So this is just a teaser. Back to our lasso. So we have this one regularization, and this is just a kind of visual aid so that you can start thinking that you understand why this works. And it works like this. So you typically have more columns than data points, so the problem is underdetermined. So your solution only of this part lies on an hyperplane. Now, to make it simple, the hyperplane is just a straight line, so you have only 2 degrees of freedom. And you want to find a solution that has the lowest L1 norm. Now, in L1, the sum of the absolute values, the sphere is a square with the vertex on the axis. So you touch the line in this point in which only one of the 2 coordinates is switched on and the other is switched off. While if you would like to have the lowest Euclidean norm, the sphere is a circle and you touch here. So if you go to n dimensions, this is always hold. The L2 spheres is a sphere as you can think of, except it is in 9 dimension. But the L1 hypersphere is always an edgy thing that always touches a linear manifold on axis. So you always reduce the dimensionality by having this regularization. What we actually did is not exactly this, because this works, this regularization is exactly solving the L0 problem if these columns here are uncorrelated. So the scalar product between pairs is not close to 1, but also the scalar products of each one with all the pairs, linear combination of the pairs, linear combination of the triplets, and so on and so forth, is not close to 1. So there is no linear correlation inside the matrix. Checking that there is no linear correlation is as expensive as doing the L0 minimization. You have to check all the possible combinations. So you don't want to do that. So you have to hope that there are not high correlations. Correlations are always there, it turns out. So what we did is to tweak a little bit lasso. So we basically go to a point in which we extract some candidates, many more than what we actually need, say a few tens. And then among these, we run the full optimization by enumeration. This turns out in some control case in which we could compare the exact solution with the actual the solution used with this method, found with this method, turns out to be a good approximation, or in many cases also found the exact solution. So this is what we found in this, published in these 2 papers with this lasso plus L0 approach. This is a chart of zinc blende versus rock salt. So we have basically what we wanted, what we asked for. Here I use only 2 dimensions because again it's nice to plot on a sheet or on a board, and we have solution with more dimensions, and you stop the dimensionality where you want to, when you achieve the accuracy that you had in mind. Now, can one find better solution than what lasso can find? So the problem is, again, the functional space in which you're moving. So we present these candidates, and these candidates, if you use this L1 regularization, even with the trick of the 2 steps with the L0, the maximum number we found that is about order a few thousands. What it means maximum number. If you go beyond that, you start getting basically kind of unstable solutions. You perturb a little bit the data points, you remove one data point, you get a new solution. So you start thinking that this is not a good approach. So we would like, but then when you construct this basis function, I mean, few thousands is not a big number once you do this tree construction, right? So you would like to have more candidates. And you easily go to billions when you start making this combinatorial trick of putting together function. So is there a way to have a matrix with billions of candidates here and few rows and still find a kind of stable solution? Well, yes. This is a recent development. So it builds on top of orthogonal matching pursuit that I present because it's easy to understand. And then I hope it's easy to understand also the next step that we introduced. So this has been basically, I guess, the first method. It's very naive to find solutions of this kind of problems. So if you look at this representation, so your property is a vector in a dimensional space, as many dimensions as data points. And your columns here, they will be vectors, of course, in this same I-dimensional space. And one of them will have the largest correlation with the property. So you take out this column, and then you calculate the residuals. So basically what is left, what this feature doesn't contain about the property. Then you look again at all the space, and you find the next feature that is mostly correlated with the residual, and so on and so forth. This method is called greedy. Greedy methods are all methods in which you construct the solution step by step, and you cannot go back and refine this solution. It finds always a nice solution. It's unlikely that it finds the optimal solution. So what we did is to say, okay, if the problem is that we cannot go back, let's have a way to go back. So instead of selecting the one that correlates most with the property, we select a bunch that correlates with the property and then calculate the residual and then select another bunch that correlates with the residual 1, 2, 3, and so on. And then we have a set of functions, of a basis function, and we run by enumeration the fit in order to find the group that best fit our data. And it doesn't have to be, and typically doesn't happen, that it is selected the best in each subgroup. It will be combinations that are in this group. This is a nice property. If you enlarge this number of things that are selected, you continuously go to the exact solution. So you know that at some point the exact solution will be there. So there is only an approximation in the number of features that you extract. But yeah. The nice thing of this is that it's trivially parallelizable. So it is good for present and future high performance computing technology. So that you can really have zillions, literally, of whatever zillions means, of property and find the best among them by running in parallel. This is the performance of this new thing compared to the old one. This is the original publication as a functional dimensional descriptor, and this is the new one. And this is this Eureka that I've shown a few slides before. We applied to the same problem, and with 10 to the 12 evaluated features, it finds this solution. It doesn't depend on the dimensionality the way we define it. With only 10 to the 11, we go much lower depending on the dimensionality. And this is okay. This is a reminder of what was found by Lasso. And with this other methodology, we find a better descriptor in terms of root mean square error of the prediction, and also visually slightly better. The green is tied to the green line. That means these are really points that are close to 0. and you see a better layering of the solid red and open red, that is those that are most stable in zinc blend, zinc blend, and those that are not so stable in terms of difference in energy. So, I mean, we looked for a better solution, we found a better solution. The descriptor is a bit more complicated. This is the price. Another interesting, or maybe the most interesting thing of this methodology, this CISO methodology that was interested, this is basically the main developer, Runai Ouyang. He will be tutored hopefully this afternoon, so you can meet him, is that instead of the root mean square error of some linear function here, you can plug in a very different cost function to be minimized, and playing the same trick with the regularization. So I put this plot as a reminder of what was obtained in the past. Now, differently from this prediction between rock salt and zinc blend, this is more classes. So it would be difficult to have on the same plot a linear prediction with more than one class. So you just want the classification. And you want to find area where something is rock salt and zinc blend. So this was solved by intuition. What is not nice here is, for example, that this area are not convex. So that you basically do not really know what happens at the borders. So turns out that it is somewhat easy to write down a cost function in which you ask for convex areas that are not overlapping as solution of your problem. So what does it mean? For in all possible descriptor representation, and I always talking about billions or more, question is there a two-dimensional or three-dimensional representation in which the data live in convex area that are not overlapping? Yes, these things can find it. This is one representation. These are rock salt zinc blend and cesium chloride as found by Runai. The descriptor is using only the radii, the same as was in this previous work. There is also the d orbitals, okay. A bit more complicated formula. It's, I would say, impossible to write this down by intuition, but this solves exactly the problem that we wanted in this way. So new points that you have not seen before, if they land in this area or this area, you know what they are classified. If you land outside the area, also this is an interesting outcome of the model. It tells you that most likely there is something that you have not seen yet. I mean, it could be that if a point land here is just a rock salt and you have to enlarge the boundary, but it could be that if you land, suppose that you didn't know cesium chloride and you land here, it could be that there is another structure that you have not seen. We actually tried. We didn't say anything about cesium chloride to our training, and the materials that are cesium chloride landed outside. So it doesn't have to be. But if the descriptor that is found has understood enough physics about the problem from the data, this could be. So this is a way to find new materials, because if they land outside, it's a blinking light saying, look at this material, do a DFT calculation, because I don't know it. It can be interesting. So these are interesting application of this methodology, so beyond the kind of guinea pig example. And here we try to find out whether the material is a metal or non-metal only by its formula. We limited ourselves to binary material, and actually, as you see from the data set, this comes from Springer material, so we didn't want to discuss whether the DFT level was good enough, if the K-point mesh was good enough to say whether something is metal or non-metal. We used experimental data. So the materials turn out to be, in order to solve the problem, they have to be 3D really, so not layered materials with some other little constraint. But in principle, most of the binaries are classified in, should be written, I haven't. So in 15 different prototype structures. So it doesn't have to belong to a specific crystal structure. So this information is contained in in the formula, but we actually use this information. As you see in the input, there is a ionization energy, electronegativity. These are property of the atom, but we also use information from the material itself. So this is a much harder property to learn with respect to the crystal structure classification. So we use information of the material. And this was the outcome as found by Runhai. So we have this two-dimensional descriptor that found two non-overlapping area. In the training set, the prediction is 100%. So the model is 100% correct. And this separation line I will not discuss too much, is more for graphical purposes. What actually the model finds is the two convex non-overlapping areas. And okay, it classifies what was put in the training set. There is an interesting out-of-set prediction. So these 3 points were the only 3 in the database in which we have the same composition. You see this one and so on. But the material was with a certain volume non-metal, and with a smaller volume was a metal. You see that there is an explicit dependence on the cell volume here. And these 3 materials were correctly predicted. So all the training set was using information at room pressure and temperature. And these materials are metals at non-room pressure. So this is prediction. So the descriptor most likely has understood enough to do this kind of prediction. Other application is the prediction whether a certain class of quasi-2D honeycomb materials are or not topological insulators. This was done mainly by Carlos Acosta, a PhD student that stayed at the Fritz for 1 year. I mean, visiting from a group in Brazil. Christian Carbonio also was involved. I think you will hear talks by him in the next days. And Runhai was again involved. So here you have this material. The blue and red are A and B. So these are material taken from the second versus sixth, third versus fifth group. And you have hundreds of them. And they are functionalized by halogens here. So we run the methodology, and we find the topological insulators of 2 different types. This was a labeling that we put, so the descriptor could find them. I will not go into the detail what is type 1, type 2. What is interesting is that the descriptor here depends only on A and B, so not the functionalization, and the other dimension depends on also the functionalization C. So basically, whether materials are in this class 1 or one of these 3 classes doesn't depend on the functionalization. So some material are always topological insulator independent of the functionalization, and some other you have to look into the functionalization. Also here we have prediction completely out of the sample. So it turns out you can construct the same materials by putting together A and B from 4,6 and 5,5 functionalized with the sixth group. So quite different from before, where they were functionalized by the 7th group. And well, the descriptor applies. It predicts some topological insulator here of type 1 and 2, and some metals. We tried with DFT calculation, and the prediction is correct. So we are predicting novel materials in this case. This is purely DFT, so we don't have yet the experimental outcome, but still a good prediction. So now in a few minutes, I should have been faster, I will introduce subgroup discovery. So this is a methodology to find local models. How does it work? The best introduction is by example. Let's say that you have a property on the y-axis of some data points that are described by one control variable. These are points that are scattered here around. You want to do a linear model out of it. Okay, you have the straight line here. Not a very good model, I would say. If you look into the data, you may notice that if you focus on this area here, where data have this control variable smaller than 0.2, these points are on a line. So for this subgroup of data points, there is a very simple correlation law from the descriptor to the property. That is actually a flat line. More complicated. Now you have 2 control variables. The second one is just a classification and is circles versus square. Now you notice that if you focus on circles up there of things that are bigger than 0.8 according to the first variable, also you have a simple classification. And you write down in this way. So if x1 is bigger than and x2 is equal to a, I have this kind of prediction. This is also a local model. What subgroup discovery tries to do is to find these subgroups and their law by just looking at all possible subgroups. Not true. It tries to crawl the subgroups in a clever way, because again, all subgroups is a combinatorial problem as it was in compressed sensing. It has some grammatics, so you have a population that would be here, some target variable, you decide which one you want, some descriptor variables, high dimensional typically, and you want to find proposition. Proposition are like this: x1 is bigger than, x2 is equal to, something else is in between certain values, and so on and so forth. And then you have an objective function that you want to optimize, such that from all possible subgroups into some value of the function, you actually optimize this. How does this objective function typically look like? First of all, there is always the size of the subgroup as a penalty. So if the subgroup is too small, you don't get a good objective function, and this is obvious. Otherwise, if you don't put this, you always find that each data point is a model by itself, and you always find a perfect model for each data point. So you have to put a penalty on the size. Oops. The other part is the part that which you really are interested in. So, for example, this typically look a bit strange on paper. One has to think about. So you want to find the reduction of ions of the population of the subgroup compared to the whole population. In this case here, if you look at the projection on the y-axis, and you think that here you have a group of points that have no variance and the other group of points that has no variance, you want to discover this subgroup, for example, that are very narrow for this property. This was applied to the Roxol-Zingblend classification. So the objective function was actually using Shannon entropy, okay, just a way to really do the thing mathematically. In practice, the idea is really that we want to privilege subgroup in which they have the same classification. And this is what the methodology found. You have Zingblend versus Roxol. Now, the way these are described, since we are not anymore predicting the difference in energy, but just the classification, is much simpler. And so one can have a lookup table very quick in which you compare this RP and RS and decide whether the thing are or not Zingblend or Roxol. There is some outliers. And the interesting are in between the two groups. So it is not bad that the method didn't see the difference. Very quickly, the last example in which you see that this methodology is very, very flexible. So here we had molecular dynamics of gold clusters. I already introduced the gold clusters in my talk on Friday, so it shouldn't be new to you. We were looking at whether the cluster were planar or non-planar. With that same data set, so this is really the data mining in which we try to find new things that were not exactly the purpose for which the data were put together. We looked at different properties using different descriptors. So number of atoms, the total energy of the cluster with respect to the most stable structure. And the interesting ones are these ones. We use the coordination histogram of the clusters. If you think how many 2-fold, 3-fold clusters are there and you make an histogram, you can have properties of this histogram thought as a function and some other suspects. What was the problem? We wanted to check an hypothesis. There is rumor that something that is called chemical hardness, that is defined here, I guess. So is half of LUMO minus HOMO, is correlated with the stability of the cluster. So this is with the relative energy with respect to the global minimum at that size. We stretched the definition. I mean, the observation in the past was about local minima. Here we use all clusters that are not necessarily minima. As you see, it's not true that there is a linear correlation on the whole data set. So we asked, is there a subset in which there is a strong linear correlation? Yes, there is. This subset here was identified there is a pretty good linear correlation between the two properties. And it has a weird definition. So it has to have that the van der Waals energy of the cluster is not very high. I mean, not very high means smaller than a certain value. It has to be even numbered, and the mode of this distribution is smaller than 5. So the peak, the largest peak is not bigger than 5. So for this kind of cluster, there is a strong linear correlation between these two properties. So this is absolutely something you would never find, this three-dimensional object here, to say that there is a high linear correlation. So you check hypothesis by using this methodology. Now, this I will not talk because basically this afternoon you will see an application. So basically you will redo tutorially the prediction of rock salt versus Zinkblende and other crystal structures. And this will be done by using the Nomad infrastructure. So basically we'll be saying this thing in the afternoon. So I will skip some slide that you will see this afternoon, no problem. Oops. I leave the summary here, and thank you for your attention.